Hi class, today we're going to be talking about the derivative of polynomial functions. And up until now we've been using the limit to calculate the slope of a tangent, which is just another word for derivative, or another way of describing derivative. But today we're actually going to be finding out what the rules for derivatives are, so we no longer have to use limits. So that's exciting. So first of all, I'm going to show you this little demonstration to get you thinking about polynomial functions and their derivatives. So the red is the function, and the green is the derivative function. So I let f at x equal x, and I let g at x equal f prime at x. So the g at x will always come out to be whatever the derivative of f at x is. So notice that the derivative of just the function x is equal to 1. And that makes sense because no matter where you find the slope of a tangent on the line y equals x, the slope will be 1. So that's why the slope is constantly at 1. So notice though if I do x squared. So the slope, so we found the derivative function of x squared yesterday. So we know that the derivative of x squared is equal to x. So notice that the derivative of a quadratic function is a linear function. Okay, what about x to the power 3? Well, notice here, the x to the power 3 has a derivative of 3x squared. That's interesting. What do you think x to the power 4 will be? 4x cubed. So there's a 4 as a coefficient, and this exponent is to the power 3. So now make a conjecture what you think x to the 5 will be. Let's try it out. Look, 5x to the power 4. So it looks like we're taking this exponent and making it a coefficient, and then the exponent is now 1 less than before. So let's try like x to the power 20. Yep, same thing. So now 20 is the coefficient, and our exponent has reduced by 1. So that is a rule for finding the derivative of any polynomial expression, x to the power n. So now we're going to go through to our note and actually do a bunch of proofs to develop some rules. Okay, so proofs are, it's really good for you guys to understand how proofs work, and then we're going to use the actual derivative rules to calculate some derivatives. Okay, so derivatives of functions are of practical use because they represent instantaneous rates of change. Computing derivatives from first principles is tedious and time consuming, as you found last night, or actually yesterday in class. So let's develop some rules that simplify the process. Okay, so our first one is a constant function rule. So if you have a function that is just equal to a number, its derivative will always be 0. That's what this says. So that makes sense because, like, let's say, for example, if f at x equals 3, that's just a horizontal line at 3. So the derivative is just the slope of the tangent. And the slope of any tangent that you could create on a horizontal line would just be 0. So visually that makes sense. But let's actually prove it. So we're going to use first principles to prove it. So let's remember that the definition of the derivative is the limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, so now let's sub in the function. So the limit as h approaches 0, so this is just k. We're going to be letting the function itself is just k. Oops. I just want to show a little bit more up here. Where'd you go? Yeah, so f at x is k, so then k plus h minus k all over h. Okay, so the limit as h approaches 0. Okay, so now you might be thinking that, sorry, this should be f at k plus h. So you might be thinking that k, you would just subtract k, and then the h's cross off, and you would get 1, but that doesn't make sense. So y is f at k plus h. What is that actually equal to? Well, let's say that we let you pick any point on here as k. Okay, remember h is just some small value that you add to be however far away you are. So if you actually, no matter how big your h is, your y value is the same as it was before. So f at k plus h is actually also just k. Because no matter what x value you put in, even if you add h to it, you still just get out k. So this actually gives us 0. So that is the proof that the derivative of any constant function is just 0. Okay, now we're getting to the power rule. And this is saying what I was showing on GeoGebra. So if you have x to the power n, where n is a real number, then the derivative is you just take n down and make n a coefficient and reduce the exponent by 1. Okay, and then this is the Leibniz notation. So for example, if you have x to the power 5, the derivative is 5x to the power 4. If you have a square root function, you can rewrite this as x to the power 1/2. So then the derivative is you bring down a half and reduce this by 1. So 1/2 minus 1 is equal to negative a half. So remember that negative exponents means that you flip the base. So that's 1 over 2 times x to the 1/2 or root x. So the derivative of root x is 1 over 2 root x. So to prove this, we need this binomial theorem here. So the difference between a to the n minus b to the n. So we actually developed this in grade 11 using Pascal's triangle, if you recall. But I just kind of developed it again for you here. So if you look at the progression of a minus b, and then a squared minus b squared, a to the power 3 minus, etc., you can see that a pattern develops leading up to this theorem, which is that a to the n minus b to the n is equal to a minus b times a to the n minus 1 plus a to the n minus 1b plus a to the n minus 3b squared. So basically the exponents on a get smaller and smaller, and the exponents on b get bigger and bigger. Okay, so we're using that mathematical knowledge in this proof. Okay, so the limit as h approaches 0 of x plus h to the n minus x to the n all over h. That's the derivative that we're trying to find. So we're going to use this binomial theorem above to expand this, because where a is now x plus h, I apologize, where a is now x plus h and b is just x. So you get here, again, the limit as h approaches 0 of a, so x plus h, minus b, so minus x. Okay, times, now this is going to be some huge thing, a, so x plus h to the power n minus 1 plus bracket x plus h to the n minus 2 times x plus bracket, or sorry, dot, 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 all the way to x to the n minus 1. Okay, so what happens here is, and then we have this all over h. All over h. So check out what happens here. I'll change the color. So the x minus the x cancels out. And then you have h times all this junk divided by h. So the h and the h now cancel out. So you're left with the limit as h approaches 0 of x plus h to the n minus 1 plus x plus h to the n minus 2 times x plus x plus h to the n minus 3 times x squared, right? And then all the way to x to the n minus 1. So what can we do with all of this? Well, first of all, we can think about actually evaluating the limit now. All of the h's now go to 0 because we don't have that division by 0 anymore. So we can actually evaluate the limit. So this actually becomes x to the n minus 1 plus x to the n minus 2 times x plus x to the n minus 3 x squared all the way to x to the n minus 1, because all of the h's have now, I can show that, all of the h's have, we've put them all to 0. So we've evaluated the limit part. Okay, so now we have to think about what does this create? Well, obviously this is still just x to the n minus 1. What does this do? Remember that when you're multiplying powers, you add the exponents. So x to the n minus 2 times x to the 1 is x to the power n minus 2 plus 1, so that's also n minus 1. Okay, same thing happens here. You're also going to get x to the n minus 1. So because of the nature of these combinations, all of them are now going to become x to the n minus 1. And then how many of these are there? How many different sums are there? There are n of them. Okay, so there are n x to the n minus 1s. I know that's not proper grammar, but it's the best we got. So that gives us the expression n times x to the n minus 1. And that's the proof. So in math, we can put a box like that to show that we've proven something. Okay, so the derivative of anything x to the power n, any function x to the power n, has a derivative of n times x to the n minus 1. There you go. Okay, we're going to prove still 2 more. We're going to prove the constant multiple rule and the sum rule. Okay, the constant multiple rule basically just says if you have any coefficient on your function, you can just find the derivative of the function part and then multiply it by the coefficient that was out there. So for example, 3x squared. We can look at this as 3 times x squared. So when we take its derivative, we can just take 3 and then take the derivative of x squared. So we keep the 3, and the derivative of x squared is 2x. 3 times 2x is 6x. So the derivative of 3x squared is 6x. Okay, similarly here, if we have y equals 1/2 x to the power 6. So our derivative then is just 1/2 times the derivative of x to the power 6 with respect to x. So 1/2 times 6x to the power 5 is 3x to the power 5. So we have a relatively simple proof for this. It won't be too long, okay? So the derivative, f prime at x, is equal to the limit as h approaches 0 of f at x plus h minus f at x over h. So that's the definition of a derivative function. So that gives us the limit as h approaches 0 of k times g to the x plus h minus k times g at x. Okay, so we're just now saying that instead of calling it f at x, we're just saying it's k times g at x, where g at x is like that inner function all over h. So we can common factor out the k. And if you recall from chapter 1, our limit rules tell us that now we can bump k out of the limit. Okay, so now we just have, So now we just have k times this limit, and we know that that limit can be rewritten as g prime x. because that is the definition of g prime x. So there you go. That's that proof. Okay, one more, and this one uses kind of a fancy little algebra trick, so that at this stage I wouldn't ask, you wouldn't be expected to be able to figure out what this trick is, but I do expect that you're going to understand what I'm doing. So the sum rule basically just says if you are adding two functions together, then the derivative is just the sum of those two derivatives. So if you have x squared plus 5 to the x, the derivative of this function will just be the derivative of x squared plus the derivative of 5x. So the derivative of x squared is 2x to the power 1, and then 5x to the power 0, so just 2x plus 5. Okay, so we're going to let p at x and q at x be the two different functions. So then at the prime of f at x is equal to the limit as h approaches 0 of, okay, so then our first one is p at x plus h plus q at x plus h, right, minus, and then another set of brackets, p at x plus q at x, okay? Since the function f at x is defined by p at x plus q at x all over h. Okay, so this is just the definition of the derivative seen above, of the function seen above. Okay, so now what are we going to do with this? So we're going to do some moving around, okay? So I'm going to take the limit as h approaches 0. Okay, so now I have p at x plus h minus p at x plus q at x plus h minus q at x. So I just distributed that negative. And this is all just addition, so I know it's commutative, which means I can just move it around. Okay, so now I can just use my rules of limits to break this into two different fractions. So p at x plus h minus p at x over h plus q at x plus h minus q at x over h. Okay, and so now my limits tell me that I can actually break, so this is one big limit right now, but I can break this into two smaller limits. So the limit as h approaches 0 of p at x plus h minus p at x all over h plus the limit as h approaches 0 of q at x plus h minus q at x all over h. So this is just the exact definition of p prime at x, and this is the exact definition of q prime at x. So there we go. So we've gone through and shown that the derivative of the sum of any two functions is just the sum of the derivatives. And we can put a little box, or you can write QED. All right, and the difference rule, so basically if you're subtracting two functions, the proof is very, very similar to the proof of the sum rule. In fact, it's the same, basically, just with subtraction and set. All right, so there we have some rules. So now let's actually do some examples a bit here. Okay, so this function here has, okay, so 4x to the power 3. So for this, we can keep the 4 out front, and then x to the power 3, its derivative, we take down the 3 and reduce the exponent by 2. And for this, you subtract 3, and again, root x here can be rewritten as x to the 1/2. So its derivative is 1/2 x to the negative 1/2. Okay, so this is what we call the raw derivative. It's not actually simplified, so we want to simplify it further. So this gives us 12x squared minus 3 over 2 root x. That is how we would want to leave it. Okay, so now it looks like we can do this derivative, but we actually can't. We can't just bring the 2 down here and make this 1, because inside we have a function. We haven't learned how to do that yet. So we have to FOIL this first before we can find the derivative. So y is equal to 4x squared minus 28x, right? Yep, plus 49. Okay, and now we can take the derivative. So that gives us 8x, because 4 times 2, and then minus 28 is the derivative. Okay, notice that it would not have worked if you would have done y equals 2 bracket 2x minus 7. Okay, so because that gives you 4x minus 14, which is not the derivative. So that does not work, and you'll learn why later on. Okay, and this g at x here, we want to rewrite. So 2 plus x to the 5 over 3. Okay, so now we can find its derivative. So g prime x, well, this is a constant, so we know that its derivative is 0. And for this, we take down 5/3 to become a coefficient, and we subtract 1 from 5/3, so 5 over 3 minus 1. So that gives us 5/3 x. So think, if we're subtracting 1, that's subtracting 3 over 3, so our coefficient is 2/3. So we can rewrite it as 5/3 and then third root of x squared if we want to, or we can just leave it like this. Okay, so this function here, we will learn something later called the quotient rule, which tells us how to find the derivatives of quotients like this. But right now we don't know how to do this. So a strategy to find the derivative now is to first break this up into two different fractions. So minus 2x squared over x plus 4 over x. Okay, so the first part can be reduced to minus 2x, and then we have to leave it as plus 4 over x, but we can write it as 4 times x to the negative 1. Okay, remember that 1 over x can be written as x to the negative 1. So now we can take this derivative. So this has a little imaginary 1 there. So 1 comes down to be minus 2x to the power 0, and then plus, right, negative 4x, and then minus 1 is negative 2. So x to the power 0 is just 1, so this becomes just negative 2. And then we have subtract 4 over x squared, because x to the negative 2 is the same as 1 over x squared. So that is our derivative. Okay, one last example, and then you guys get to practice before coming in tomorrow. All right, so determine the equation of the tangent to this quartic at x equals 1. So we need the equation of a tangent. Remember, that's just the equation of a line, so y equals mx plus b. So we need m first. So remember, the slope of a tangent is just the derivative at 1. Okay, so let's find f prime at x first. So x to the negative, so negative x to the 4, so we would have negative 4x to the 3 plus, so 2, so we'll bring down the 3, so 2 times 3 is 6, x squared minus 1. Oh, sorry, nope, because the derivative of a constant is just 0. So this is our derivative. So if we sub in 1, we get minus 4 times 1 to the 3 plus 6 times 1 squared. So we get 2. So the slope of the tangent at 1 is 2. So now our equation is y equals 2x plus b, and we just need to solve for b. So we know that x is equal to 1, and then we put 1 into the function to find the y value. Not into the derivative, but into the actual function. So if you put 1 into that function, you get 0, I believe. 0. Yeah. So it's an x-intercept. That's interesting. So then you get 0 equals 2 times 1 plus b. So your b is -2. So your equation of the tangent is y equals 2x minus 2. Oops, that was not a good circle. You guys can draw better than that. Okay, so now I have some practice for you guys, just some simple ones for you to try. So remember, for 1, you can just take the derivative. For this one here, you're going to have to FOIL before you can take the derivative. For this one, you should rewrite the square root with a rational exponent. And for the last one, you need to write it as 2 separate fractions and then with negative exponents before you can take the derivative. The success criteria are down here, so you can take a read and come ready to work tomorrow and find lots of derivatives. So thanks for watching, guys. I hope you learned lots.